Hi everyone. So this is a problem that I would consider medium difficulty torque and forces problem. It's a pretty common kind of problem. You've got a 15-meter long ladder. It weighs 50 newtons. It rests against a smooth wall, so there's no friction on the ladder from the wall, um, making an angle of 50 degrees to the horizontal. If it's just on the verge of slipping, you'd like to calculate the coefficient of friction between the ladder and the floor, which is needed to just hold it in that position. So this is medium because a lot of times you have a person standing on the ladder, and sometimes the wall has friction, different things like that. So in any case, this kind of gives you the flavor for how to start this kind of problem. So what's important is to make sure which angles you have in the problem. They're telling you 50 degrees to the horizontal. What will also be important later is to realize that this angle to the vertical is 40 degrees. We'll see why in just a little bit. So again, in all your problems, you want to start with a free body diagram. And sometimes these problems have some forces which we might not have encountered before. A lot of times from the surface of the wall, we call it a normal force, but to be more descriptive, I will say the force of the wall. Now the wall can only push perpendicularly to itself, so the force from the wall on the ladder at point of contact will be directly to the left. The weight of the ladder we choose at its center of gravity, which if you split the difference, if it's a uniform ladder, it's going to be right in the middle. And then, of course, the wall has to push directly up, or the floor has to push directly upward on the ladder. That's typically what we'd call the normal force, right? And then what's holding it from slipping, right? The ladder wants to slip to the left. So the force of static friction must be holding it rightward. So that force is going to point to the right. Those are the only four forces that are acting on the ladder because they tell us the wall is smooth. Otherwise, there could be a force of friction, holding the ladder upward or something like that on the wall too. But in this case, we don't have that complexity. So the next thing is to write our T-chart, as usual. And so we've got the normal force directly upward. We've got friction directly to the right in the x direction. We've got the weight of the ladder downward. And we've got the force of the wall pointing directly leftward in the x direction. So this allows us to write the sum of our forces in our x direction, the sum of our forces in our y direction. Now remember, the goal is to find mu sub s. So we're going to have to find that from the force of static friction. But there's some other forces we don't know, like the force of the wall, right, and things like that. That's where our torque equation is going to come in handy. We're going to need it, actually, in this case, because there's, well, we'll see. So since mu is an unknown, right, and it's in this equation with this other unknown, and there's no other way to get to this from these equations, we want to pick our point of rotation O so that we can eliminate the thing that we're looking for. That helps in a lot of problems. So we choose that point of rotation of the ladder at the location of F sub s, the force of friction. Because the lever arm to F sub s is 0 from that origin, that will eliminate it from our torque equation. So it'll help us right away. So right here you can see I'm choosing O to be right here at the point of contact with the floor. All right. Then both the normal force and this force have a lever arm of 0, which makes their torques 0 about that position O. All right. So we want to write our net torque equation then. So the only two torques we'll have are from the wall, right? At the lever arm are that the wall is pushing on it from O, right? Sine of 50. So you can see that the angle that's being made here is 50 degrees with the horizontal, okay? So that's why it's 50. Plus it's acting counterclockwise about point O, so that's why it's positive. The gravity force, okay, is acting to rotate the ladder clockwise, so it's going to be a negative torque, and it'll be the weight times its lever arm, which is half the ladder length, right, sine of 40, because its angle that it makes to the position vector is 40 degrees. All right, so that's our symbolic torque equation, and here I'm substituting knowns that were given in the problem. They told us the length of the ladder was 15 meters. That's the position that the force is being applied from the wall. And since the weight of the ladder would be at its center of mass, that's half the length of the ladder, so that'll be 7.5. And they did tell us that the weight of the ladder is 50 newtons. So substituting in, you can see that we can solve for our unknown, which is the force of the wall, 20.98 newtons. Now we have to go back to the force equations. Okay, we've found something that we need in the force equations to eventually get to mu from the torque equation. So coming back to what we had up above, okay, notice this is our goal. If we rewrite this, mu sub s times F sub n for our force of static friction, we just found the weight force, right? And we can see that the only other thing we would need to find mu sub s is the normal force, which we can find from the y direction. All right, and that's 50 newtons. So putting all of that together, right, then we would have mu sub s times the normal force, 50, minus the wall force, and we can solve for our mu sub s of 0.420. That seems like a reasonable value. All right, that's kind of a long road, but that's kind of how the whole thing works, and so hopefully that makes some sense.